Hello and welcome everyone. Our first lecture on climatology, covering chapter 1 from our book. Um, really just diving in, climatology 101, weather versus climate. This is often the very, very first thing that you have to discuss with people when you start talking about climate is the difference between weather and climate. So hopefully this will be really good. First off, though, I always love starting the class off with something like this. I call them the fun fact for the day, FFTD. This is something my undergrad instructor and advisor did, and I just loved it every time. And although mine tend to be more about maps versus birds in her case, but yeah. So this is. But we all know the saying, and I'm sure you've all claimed it for even your home place. We have the wildest weather. Just wait 5 minutes and it'll be different. Well, my buddy, Brian Brettschneider, who created this map, he's up in Alaska. He's a climatologist there. Good friend of mine, and he generated this map not long ago to kind of just see where is the most extreme temperature changes anywhere in the United States, and he used some data sets. We're going to be talking about data sets and how they get used next week. But he used this ASOS temperatures from the Mesowit that's now hosted at Iowa State. It used to be at Utah State. But he basically took that whole big data set and generated the 99.955th percentile. So the most extreme 5-minute temperature change. It's most extreme, but in all honesty, there's a lot of 5-minute time steps in a day, right? So it's actually what you would expect to happen no more than one time per week. That's what the laws of probability say. And he generated this map, sort of what is the most extreme 5-minute temperature changes, observed from this set of data points, and it is remarkably cool, I think. So here we are, at least some of us are down here in Southern Oregon, and so we're kind of right on the cusp. Actually, we're squarely more in the orange, although folks in Klamath are just on the other side of the Cascades or in the green. So in our case, we can have a 5 to 6 degree Fahrenheit change, which is huge, right? That's pretty big. That's a noticeable change in 5 minutes. But man, look at how impressive it is out in the Rockies and the plains. It's kind of remarkable. So I went to school in Gunnison, which is about here. There's no station for it. And I grew up in Littleton, which is definitely the southwest side of Denver. So right here. And I grew up hearing that, oh yeah, if you don't like the weather, just wait 5 minutes. And I thought it was really absolutely like the truth for Colorado. Well, this is the first time that I've actually had validation that, yeah, actually in Denver or most of, sort of the central part of Colorado and as well as northeastern Wyoming and into Montana, you can have an over 9 degree. That is a tremendous change in weather in 5 minutes, right? But it's happened, and there's lots of good data to support it. I know just this last year, in November, I think it was, all my friends in Denver showed a picture of their thermometer in the morning where it was 70. No, in the morning there was snow, and by the afternoon it was 74 degrees. So in the morning there was 32 degrees. By the afternoon, just a couple hours later, it was 74 degrees. So I totally believe it with things like this. So your fun fact of the day, yes, weather can change over a 5-minute time period pretty dramatically, but more so in some places than in others. And yeah, the West is pretty quintessential with our basin and range and all the mountain ranges and the deserts that we have. It's not a super surprise that that's where it's identified. And interestingly, not a huge amount of change in Alaska, although you'll see the stations, there's not very many. But the one, right outside of Anchorage is fascinating. So yeah, Eagle River, Wasilla, Palmer, sort of the Matsu Valley up there can have an 8 to 9 degree change. Pretty fun. All right, Weather 101. Hopefully you guys remember this from basic kind of earth sciences, but it's always good to just get a brief refresher. Remember that weather is the instantaneous state of the atmosphere. So it's what you feel at that moment. So there is short-term variation, like the fun fact for the day, right? You can't have 5-minute wild swings in temperature, which is cool. But that makes it is very hard to predict. All of the best models that we have still can only predict weather 72 hours in advance with any sort of accuracy. Beyond that, they're really taking climatological data and sort of adjusting it. They're not doing full-on predictions. Computers just, even today, still aren't powerful enough to crunch all those numbers, and we just don't understand the individual manifestation of weather well enough to predict it with any kind of certainty. So think about that. It's funny, always newscasters always do the 10-day forecast or 7-day forecast or whatever. I mean, really, just pay attention to the next 2 days, and accuracy goes down tremendously. By the third day, and even the second day, it's worse than the first day, right? So weather is instantaneous, and because it's instantaneous, it's very, very hard to predict. These are the variables that we tend to think of, temperature, precipitation, humidity, right? That's something that we don't see on the climatological side. Air pressure, cloudiness, radiation, wind, and visibility. This is what we typically see. There's a whole host of other things that can be measured with a weather station, but that's what you typically see. And just as a quick plug, we've got one here at SOU that we've managed for the last 15 or so years, 15, 16 years now. You can visit it at weather.sou.edu, although right now we can't because, as you'll see in this picture, it's solar powered. And unfortunately, given that it is 16 years old, that solar panel is now not producing enough energy, especially in these cloudy days, to actually charge up the battery enough to run all the equipment. So if you go there, it's going to show some really funky numbers that haven't adjusted for the last 3 days. We're on it. I manage this with Dr. Smith, and we run out there and we check on things pretty constantly. But we do have a website. It runs on Flash right now. It's being updated too. But no, we have this, right? It's really cool. And this is what we typically present: humidity barometer, so that we get the air pressure. We have sun and moon cycles too. That's just for the fun of it. We have estimated evapotranspiration, which is really key. The station is located there in the field of ScienceWorks. So this is Main Street in the background, I believe, or that's Walker. I think this is Walker. Over here is Main Street. ScienceWorks is over here, the building. So it's right next to the farm too, the SOU farm, and the Ecos Community Garden, and all kinds of things, right? So having estimated evapotranspiration is really, really key. But we do temperature, dew point, solar radiation. That's measured up here with the insolometer. We have a precipitation gauge. You can't really see it. It's down here. Measures, and accumulates for the annual and the monthly. Look at this, guys. And this was taken December 30th, just a couple days ago. And our annual precipitation is not great. And it's got monthly precipitation, although our rain gauge is a little wonky, so don't take that too seriously. And we've got monthly and daily then too. We've got wind speeds, again, instantaneous things, right? So when this website is up and running, working, you'll see this change every 3 seconds. That's how fast we're sending information. And then it's all located there. So remember, it's a specific place as well. So it's instantaneous in time, but also instantaneous, or it's a very specific place. So we present very upfront on the website, this is the latitude, longitude, and the elevation for this station. And that's really important because that station doesn't represent the weather that's downtown in Ashland, or the weather that's on top of Mount A or Grizzly Peak, or even down by the river, right? Less than a mile away from the site. So it's for there. It is built to a specific height. 20 feet is what NOAA and the Weather Service really want for wind speed. And so it meets all the specs of getting the temperature at the right level so that they can update their forecasts and collect proper data. So something cool. Once it gets up and running again, we'll spend more time with this. So that's weather. Then we have climate. And climate is simply the statistics of weather. So it's how we look at longer term trends. And we mostly think of this in terms of averages, that we either average over months or years or decades or centuries or even more, right? Millennia sometimes. But it's an average, or it's some sort of statistical summary then of weather data. Because of this, it can include probabilities of extreme events, because it's all statistics, right? We can do things like normal distributions and figure out what the statistical probability is of an extreme temperature based on, recorded temperatures from the last however long you want, months, years, decades, and so on. When we talk about climate and we're talking about climate change, that means we're comparing one climate to another, right? And so when we talk about climate generally, we are thinking in terms of 30 to 40, but really just 30-year time periods, that when we say, oh gosh, we're 10 degrees above normal, it's the 30-year time period prior to your current decade. So we're now in 2021, which means brand new climatological data just got released a couple of days ago, and I'm going to be featuring that over the next couple of weeks, where they look at the year 1990 to 2020 as our climatological average. So that's our new updated climatology. That's different than what we were working with for the last 10 years, right? Which would be 1980 to 2010. That was the climatology that we were comparing for some of these extremes. We'll talk a lot more about this in general, but just remember that we're looking at data or weather data from a statistical perspective. So we plotted out a standard kind of histogram here, right? Or probability distribution function, where this would be your average temperature, or precipitation or whatever, and we can calculate then based on the tails, right? First standard deviation, second standard deviation, third standard deviation, the probability of getting a certain temperature. So that's really what it is, and we can do this testing, changes in variance or increases in mean and all this kind of stuff. And this is how we're arriving at the conclusions that there's more hot days. It's actually shifting the distribution of the data, the probable distribution of data, because we're seeing the average shift a bunch and sometimes the variance shift a bunch, right? So I'm sure you've all heard sort of more extremes, where it's warm already, it's going to get warmer, and where it's cold already, it's going to get colder. Well, this means that the variance is expanding, right? We're getting less of a tight little hump of data. We're expanding out the data, which makes it really, really challenging, right? To say that climate change is one thing or another, because it's variable. But we have the statistics to kind of discuss that. So that's climate. Because it's basically statistics of weather, it means that climate is actually more predictable than weather. So weather is based on all these instantaneous factors that are really hard to capture and model in a simulation. Well, climate's just summaries of data. And so once we have that, we can start to explore things called forcings, things that we think are driving the temperature or precipitation or the climate data that we're seeing, the averages and whatnot. And this is key. So thinking back to, hopefully most of you have taken data analysis, or if not data analysis, at least, Math 243. But if you think about a regression, right, the whole idea is that we're taking some predictor, some data that we think influences another data. So with temperature, say one of the forcings that we want to look at is solar radiation, the amount of solar energy coming in. Well, we can take temperature and we can plot it against solar radiation. And then we develop a regression and we say, oh, sure enough, they're correlated. And you run the regression, you get a p-value, and you say, oh, yep, they are absolutely related. And so you hypothesize that as a forcing, you do some experiments and so on and so forth. So climate is much more predictable than weather. And that's a really key point. So if you were to go and sort of Google Ashland climate, this is the first hit that you're gonna get. You're gonna get this little thing come from usclimatedata.com. It's not super clear where they get their data from. We'll get into that more in a second, but this is what you might expect to see. If you Wikipedia any community that you think you're going to move to, you'll get the same sort of thing. Basically, these bar graphs of precipitation and high and low temperatures, right? So this is climate, so it's averages, right? But we don't know exactly. We're just going to assume 30-year, standard 30-year. They may or may not be a good assumption. We'll find out here in a second. But you see that precipitation generally in Ashland for January is somewhere around 2.3 inches. This is 2 inches right here. Or maybe this is 2 inches. Hard to see, hard to read this graph. 2 to 2.5 inches of precipitation. And the average high is somewhere around, oh, here it is. It's right down here. Silly me. 2.26, right? Average inches of precipitation. Average high is 49. Average low is 29. So it's calculated this simple mean statistic for the average high and the average low value across all the years for January, February, March, April, May, so on and so forth, right? So this tells you a lot about Ashland. I mean, this is the climate. It's warm in the summers, right? Both high temperature and low temperatures, the highest in the summer, and it's dry in the summers. Precipitation is the lowest. This defines the climate of Ashland, and it's simply just statistics. If you go a little different, a little deeper, and you go to the next hit on Google, you might find something like this. This is from the Western Regional Climate Center. This is also mentioned in the textbook. Western Regional Climate Center is, it's been a repository for NOAA data, or from a whole bunch of sources of data, I think for about 40 or 50 years. I can't remember exactly when they started, but it's been a long time. So, and this is at Desert Research Institute, as I mentioned. This is where I did my master's and PhD work, or I did had all my funding from them. And so they manage this database nationally. It's for stations across the nation. And so you get something that looks like this. Well, for those of you with a keen eye, you might actually see that there's a little bit of a difference. So the average high for January is 49, according to this one, and according to WRCC, it's 46.7. It's like, wow, that's different. And it's pretty different actually across the board. You see some of the average highs: 79, 88, 87, 78, 86, 85. They're different, right? Well, the first note is this one actually tells you the period of record. So from 1948 to December of 2005. So that's one thing to notice. So then you dig a little deeper, you go to the next site, and WRCC, the Western Regional Climate Center, also gives the NCDC monthly normals. And so the NCDC is the National Climate Data Center, managed by NOAA, the National Oceanographic and Atmospheric Administration. I should define that, given that we're in our first week. And so they have numbers that are different as well. So average max temperature is 46 here, and it's back up to 49 there. But you see here, it's from 1981 to 2010. This is the previous climatology. This is what we thought, or this is what we were measuring and changing, estimating our changes based on, was this climatology from 1981 to 2010. So that's the averages just for that time period, which is a shorter time period than this, right? And this is just to highlight just how different time periods can make a difference in your calculations of simple things like, oh, what is the average temperature, mean temperature. So I did a quick comparison. You can kind of actually see that this US climate data actually probably is just pulling the data from the NCDC, the National Climate Data Center, which is good. And it's just rounding down because the numbers are pretty identical. And the Western Regional Climate Center, being that it is from a different time period, does show different means, different averages. So this is key, and this has been something that's been discussed a lot in the popular science media, is that you can absolutely cherry pick certain periods in time to suggest other trends are happening or suggest other means. It's really important to consider what is the time period that's relevant for measuring change. We're going to obviously spend a lot of time talking about this this term. So one final thing on this climate versus weather thing. I mean, the easiest way to remember is, climate is what you expect, and weather is what you have, right? So we can expect things based on averages and laws of probability, saying that, yep, on average, we expect the high temperature any given day in January to be 49 degrees. But we know that weather varies tremendously, and weather is what you get. And so simple things like cloud cover, or therefore the solar radiation, or anything can kind of influence the actual temperature that you experience. So climate is what you expect, but weather is what you get. It's what you feel. So so just a brief on the climate system. All these parts we're going to dive into in subsequent weeks, and so this is just a quick introduction. But climate as a science is really rooted in multiple sciences. It's we have this conceptual model of how the climate works, and therefore all the forcings, right, that I was just talking about, the things that influence the climatology that we experience through weather. So this is a really simple one from Gentleman and Rood. This is that other book that I was mentioning as an open resource. We have the atmosphere. Well, first off, we have the sun, right? And the sun is the most important because that's our source of all energy. So all heat, everything that we experience is simply because of the amount of radiation coming through, coming from the sun and into the Earth's systems. And it hits first the atmosphere system. It influences, we have the biosphere system, the terrestrial, the anthrosphere, the cryosphere, which is the ice that exists, so both sea ice and land ice, and then the ocean. The book kind of says, it has this nice visual of the blue marble for describing this. I thought that was kind of fun. But remember, so the atmosphere is pretty complex. It's about 10 kilometers thick. It's divided up in 3 different sections. We're going to talk more about that later on. But that's pretty substantial, right? The ocean is obviously a hugely important part. We're 2/3 of the Earth's surface is covered with the ocean, and on an average depth of about 4 kilometers. So you can imagine that has a tremendous potential, because if you remember back to maybe high school physics, water is a temperature buffer. It absorbs energy, and it's slow to radiate it off. It's not like the desert where it immediately reflects it back out and doesn't trap anything. Water soaks in a bunch of energy. So it plays a big role in sort of the Earth's climate. And then thinking about the terrestrial, the lithosphere, the cryosphere, and biosphere, of course, all living organisms, we know trees respirate. So they play an important role in these systems. This is the one from the book, a bit more complicated, right? But these conceptual models are awesome because it's basically a graphical representation of all of our assumptions. So if you ever want to know, like, what goes into a global circulation model, well, you look at this. This is exactly what goes into a global circulation model. We have concepts of changes in solar inputs, solar radiation, right? And that varies on celestial scales. Certainly, we'll talk more about that this term. You've probably heard about solar flares and that kind of thing. So we can estimate, we measure, we model amount of solar inputs, but that's all the energy that comes into the Earth's system that determines all of our climate. So first interacts with the atmosphere. Atmosphere has aerosols. Aerosols have the potential to hold on to more heat. It also has the potential to reflect off heat. So the solar energy coming in might hit some aerosols and bounce back out, never hit in the Earth's surface. Some will let it come in. It'll hit the Earth's ground, come back out, and not leave the Earth's atmosphere. That's the greenhouse effect, right? So any change in composition of the atmosphere in terms of aerosols, or the chemistry in general, you change the way the temperature is distributed across the atmosphere. You have a lot of interaction then with the atmosphere, with water, with ice, and with land. So you get a heat exchange between the atmosphere and land, depending on sort of the reflective capability or characteristics of a land. So those of you who've taken remote sensing or maps and cartography kind of remember that some objects on the Earth's surface absorb energy and some reflect off energy, right? And this is why we can do things like normalized difference vegetation index. Well, that absorption then interacts with the atmosphere. And if it absorbs that energy, it's not going back out into the atmosphere. That changes the atmosphere. Or conversely, if it reflects all that energy back off into the atmosphere, that is an interaction between the atmosphere and the land. Same with the ocean, same with the sea ice. Really, really important. And all these coupling, all these heat stress, right? Like those are all equations within models that we've built to describe climate, to predict climate. We have the hydrosphere here, which I don't think the book really talks about, but it's obviously we have the hydrosphere as the ocean. Oceanographic is a whole week. We're going to spend some time on that later on, but we do have the rivers and lakes. Freshwater is less dense than ocean than saltwaters, right? So that has ramifications for heat trapping and heat distribution. Obviously, anytime there's ice and snow, that has big ramifications for reflectance. The reason we see ice and snow as white is because it's reflecting all that energy right back off. And then volcanic activity. I'm sure you've all heard that, every time we have any kind of eruption or the ones that are longstanding, that puts a bunch of aerosols in the atmosphere, therefore changing the chemistry of the atmosphere. It can also block out the sun, do all these things, right? So there's all these interactions, just so many interactions that are happening. We're going to talk a lot about the cryosphere interactions, this whole white turning into the hydrosphere kind of thing, because that's a really important piece that we're experiencing really, really rapidly right now. So you can kind of see how this is all laid out. And hold on real quick. All right, sorry about that. But so yeah, this is a conceptual, he calls it a schematic view of components of the climate system and processes involved with all the interactions. The key is that all of them are interacting, right? And so when we talk about predicting climate through understanding climate forcings, this is what we're talking about. All the interactions, all the factors that influence the manifestation of climate. And yes, it does all start with the sun. Absolutely, but it's all through all these interactions that we see the climate that we experience. So let's get back to that. Enough on the conceptual side. Let's look at some data, right? So in the book, it kind of recommended going off to, I think the WRCC actually, and looking at some of the, distribution functions and just looking at the data and deriving an understanding of extremes and sort of the predictability of average temperatures. And so I did that. I did that for here in Ashland, and we'll do it for a couple different places in class. But and I followed his recommendation, just May 1st, looking at high temp, right? So we could have looked at average temperature for May 1st, or we could have looked at low temp, right? We could have looked at a whole bunch of different factors, but I just did it for high temperature. So this is representing the actual high temperature readings for May 1st for Ashland. It's based on the WRCC, so it goes back to 1948, right? Or as long as the data exists for that station. And which I think is about 1948 for the station that they're using for Ashland. It's not our SOU one. I know that much. And you plot it out. So this is just a basic histogram that you do in Microsoft Excel. Those of you who've done data analysis know how to do this, right? So this is a histogram in that it shows you how many times the frequency, how many times that value between these two values was met. Actually, I hate how Excel does this, but 47 is the average of this bin. So you can think of it as some number up to the midpoint between 47 and 55 degrees. But basically, just think of it as, okay, only once did we have something near 47 degrees on May 1st as a high temperature, only once. So that's a pretty extreme temperature. We would say the probability of that happening is really, really low, right? Same, there's only 2 observations of 55. It's not until you get into this sort of realm that you start saying, okay, that's 7 observations, that's 9, that's 9, and there's 3 that are higher than 80 degrees, right? Um, Actually, summing that up really quickly in my head, yeah, we're talking only about 30 or 40 years of data here. But it's pretty easy. So it was just a matter of copying and pasting. We'll do this in class just to get some experience into Google Sheets or whatnot and creating a graph. And then this is just a cumulative function. So this shows you that really most of the data is located right here, because that's when you get to the 100% of representation, basically, is what that cumulative shows. So this is a typical climate graph. Maybe one that's a little bit more, well, certainly more appealing than the janky one that I just did in Excel, but probably also one that you've perhaps seen in other environmental science type classes or even articles before. So this shows average temperature for the whole year for Medford. So the book recommends going to this other site, a NOAA site, right? And going and figuring out how much does the variability change and the trends in temperature change when you look at different scales. All right. So remember, weather is instantaneous and tied to a geography. So it's really important when you're thinking about climate, the summarization of weather, that you think about the geography. So Medford it has records back to 1926, 27, it looks like, right? And here you've got the average annual temperature, January through December. So the average temperature year round is kind of marked here. And this is across the entire record of data in this case. 1928, yeah. So from 1928 to 2000, the average temperature in Medford annually, right? So that includes highs and lows and everything, is 53.5 degrees. And this is how each year plots out compared to that average across this whole time period. This is the recording for the year. So you see years much below, a couple degrees below. You see one really far below the mean, and then you see plenty above the mean. What this blue shows is the trend from the beginning of the time period, 1928 to 2019. This is just a simple linear regression trend saying, okay, I'm maximizing the fit of the line that best describes these sets of data, these observations. And when you do that, you get this that has a slope suggesting about a 0.4 degree Fahrenheit warming per decade in Medford. So this is Medford. This is probably the airport weather station. That's typically where the longest lasting weather stations come from, is from airports. And so that's fairly dramatic, right? 0.4 degrees Fahrenheit is significant per decade. That would mean that, for some of you who are 20 years old, that you've experienced and say live here, you've experienced a degree change Fahrenheit, close to a degree of change in Fahrenheit. Those of you who are 30, over a degree, and those of you who are 40 or more, perhaps have experienced, fairly significant changes in temperature, average temperature. So that's not extremes. That's not numbers of 100-degree days or anything like that. It's just the average temperature across the whole entire year. So that's for Medford. This is what it looks like for Oregon. Man, that didn't turn out quite as clean as the Medford one is, but same thing. Oregon, though, so averaged across all weather stations in Oregon, goes back to 1895, which is super cool. There again is the mean temperature. So Oregon-wide, the mean temperature is 46.5, significantly cooler than what it is for Medford. But we all know that. That's why we live in this region, right? And that trend then is less pronounced. It's only 0.2 degrees Fahrenheit. So when you scale up, you start to get more variability, right? Bigger variance. And so these trends become a little bit more nuanced. They're less easy to see, but still an upward trend. Same thing if you go to the whole contiguous U.S. It just does not include Alaska and Hawaii. For obvious reasons. The mean temperature is 52, so we're actually, overall, we're a little bit warmer than the average for the whole entire United States. But you look at that trend, and it's about 0.15 degrees Fahrenheit per decade. So again, even more nuanced, less of a trend when you look across a broad geography, because weather is so tied to local variables. This makes pretty good sense. I had to throw in Alaska. So we've gone from small to big, and now let's start going back down smaller. So I hope you all have heard that Alaska and anywhere north of about 50 degrees Fahrenheit or 50 degrees latitude is warming at a much more rapid rate. Actually, I think it's 60 degrees and above is warming about twice the rate of the rest of the world. And so if you look across the whole state of Alaska, which dips below that 60-degree latitude mark, you do see this 0.3 degree Fahrenheit increase per decade. You see there's pretty serious variability, right? Big swings, interannual swings in average temperature. But of course, the average temperature for Alaska is cold, 26 degrees. You look then at the most northern borough, which is the equivalent of counties in Alaska, the North Slope borough, and it becomes more pronounced. It's actually closer to what Medford's experiencing, right? 0.4 degree Fahrenheit per decade. And this is based on record going back to 1925 to 2000. So about the same record period as Medford, which is cool, huh? I mean, that's kind of big. That's significant. You see a bit more of a sharper increase at the tail end, which is really interesting. We're going to be talking about this thing called Arctic amplification here soon, or polar amplification. But yeah, pretty interesting that it kind of spikes up there. But 0.4, and the mean temperature is of 13.3 degrees Fahrenheit. But when you focus in on a specific town in Alaska, on the northern part of Alaska, specifically Barrow, that's when you start to see, oh my gosh, yeah, twice, 3 times, 4 times. It's actually 4 times the warming rate of the contiguous U.S., 0.6 degrees Fahrenheit per decade. It has a mean temperature across the whole record of 9.9 degrees Fahrenheit. And so when you start looking at the last few years, the mean temperature has been 14, 16, 17, 18, 20, 21 degrees Fahrenheit. That's significantly different than the average for the last 80 years, right? So we think about temperature trends in this way. We plot them out as average temperature across years. We also think of it in terms of this. This is the temperature anomalies, and this is where I'll leave you off with is a couple of temperature anomaly graphs. So anomalies meaning if you take that average temperature, right? Then you just basically measure, say in this year, 1941, it was 0.18 degrees centigrade warmer. Well, that then the average. So the average temperature was 56 degrees Fahrenheit, then it would be 57 degrees. It was 57 degrees in 1941. So the anomaly is basically just how much above the mean for the whole record was that year. And so you often see this graph because this is one of the most telling graphs about global climate change is you see these below normal temperatures sort of all the way up until, factories, right? Unionization of the factories being built in the 30s. And then you just see just this incredible, and this is for global land and ocean. So this is across the whole Earth. You start to see these anomalies. You have some cooling, but you still see some anomalies. But really in the last 20, 30 years, it's just been this explosion of anomalies. We haven't had a cold year in a long time, and you can calculate the trend based on this as well. It's interesting always to separate out the southern hemisphere from the northern hemisphere. So if we've got a 0.8 per decade or 0.08 per decade centigrade, trend going on globally. It's interesting that in the southern hemisphere, it's only 0.07. Still all the anomalies, the warm anomalies, are in the most recent years. But in the northern hemisphere, it's actually more pronounced, right? It's 0.09. And that's, again, tied to where the landmass is versus the ocean, right? It's tied to where all the industrial activities are. It's tied to where the volcanoes are. It's tied to all these things that I just described as part of the climate process. But we're going to be disentangling a lot of those as we go through the term. So that's our quick intro of weather versus climate. And don't worry, we're going to spend a lot more time with all these graphs. And so I look forward to doing with that with you all soon.